Atom probe tomography provides an analytical mapping of materials in 3 dimensions with a sub-nanometer scale resolution and bring insights into both chemical composition and structure of materials. This diagram presents detection range as resolvable features for different common microscopy techniques. And what we can see easily is that atom probe tomography contributes to the challenges for material science characterization at the extremes for chemical sensitivity and physical length scale. This is an example of a 3D atom probe tomography analysis of an LED structure with a tunnel junction in the GaN top layer and with in-GaN quantum well layers as optical active area. Not on this reconstruction, one point is one atom. So from that kind of reconstruction, we can extract several information, such as example, concentration profile of the dopant around the tunnel junction, showing magnesium segregation and diffusion of germanium along the top and type GaN layer. What we can do also is to calculate the in-GaN side fraction within the in-GaN quantum layers, showing variation of composition and distribution along the disk. Resolution of atom probe tomography is anisotropic, but can be subnanometric along the depth axis. All the elements can be detected in the same way, even light element, with a low limit detection around 5, 10, 19 atom centimeter cube. It is also possible to analyze local features such as devices or defects using focused ion beam equipment for specific site area preparation. And all these specifications make APT very attractive for the investigations of interfaces, impurity, density, clustering, low distributions, and obviously dopant profiling. So how atom probe tomography works? This technique is based on field evaporation of a tip-shaped sample with N wedges down to 100 nanometer, which is placed in a high vacuum chamber and cooled down between 20 and 80 Kelvin. The high steady stage voltage is applied to the tip, which induces high electrostatic field at the apex of the tip, which will lead ultimately to the ionization and evaporation of surface atoms. The ions are then collected by a positive sensitive detector with a time of flight capability. But in practical, the electrostatic field is below than the evaporation field of the chemical spaces. Evaporation is generated and triggered by ultra-short laser pulses. The chemical nature of the ion is determined using time of flight mass spectrometry. And the time of flight is measured between laser pulses and the impact of ion on the detector. And since time of flight depends on mass over charge ratio, it's possible to identify the chemical nature of ion. The 3D reconstruction is obtained using both coordinates of the impact of the ion on the detector with the total number of ions collected during an analysis associated to reconstruction algorithm. So I think now you are aware that this technique requires a tip-shaped sample. So how is it possible to obtain a tip-shaped sample from a bulk sample? We do that by using the power of the ions and especially using focused ion beam equipment. The main idea of the focused ion beam is to remove materials from sample using incident ion beam. So 2 steps are required to prepare a tip shape compatible for atom probe tomography. The first one is called lift out, and consists of the extraction of the region of interest. So before doing that, obviously the sample has to be protected to prevent damages from ion milling. Then the sample is cut part to part to part. A micromanipulator which is into the FIB is welded on the lamellar, which can then be lifted out from the substrate. And a little bit of the lift out lamellar is then welded on APT holder. The second part of the sample preparation is the annular milling of the chunk. So for that, this little piece is aligned along the beam direction, and the inner diameter of the milling circular mask and the milling current are reducing progressively after each milling stage up to obtain a tip with iron wedges down to 100 nanometers. So note that the final steps are done with a low energy to again minimize irradiation damages. So for the following of the presentation, I will show you several examples illustrating APT capabilities for semiconductor investigations. The first one will be magnesium doping in p-type gallium nitride structure with the effect of temperature and concentration on spatial distribution. The second one will be focused on InGaN quantum dot nanostructure with correlation between optical, structural, and chemical signature of these systems. And the third application will be dedicated on boron doping in nano devices to extract reliable boron distribution. And I will show you at the end some artifacts and limitations of this technique. So first example, a dedicated sample has been grown using MOCVD process to study the effect of the gross temperature at high magnesium incorporation in a doped GaN layer. The stack is made of N-dop and doped layer grown by decreasing the temperatures. And this is a 3D APT reconstruction of magnesium distribution within this sample, where a lot of interesting features can be observed. We can observe segregation of magnesium along a defect, which is a threading dislocation. We can observe the presence of magnesium within the N-dop layer, and we can also observe the presence of magnesium inside the doped layer. So it is not shown there, but we are able to calculate a size distribution of magnesium clusters as a function of the gross temperature. We are able to calculate the magnesium inside the clusters, but what we have decided to show you is this results, which is magnesium fraction outside clusters in N-dop and doped layer as a function of the gross temperature. And this is a relevant result because it can be directly related to the activated dopant that can be measured by other techniques such as electron holography. And if you want more details about this correlation, you can find an answer in this paper. So the second example is InGaN quantum dot investigations. So briefly, quantum dots are 3D quantum confinement systems responsible for light emissions. And it's possible to tune wavelength emission by varying their size and their indium side fraction. So that's why on the platform for nano characterization at CIRE Grenoble, we have developed a methodology to correlate chemical, structural, and optical properties of this kind of features using the direct comparison between simulated and experimental emission wavelengths. So this is a sample that has been investigated. So it has been grown using MBE process on sapphire substrate with a gallium nitride buffer and with a stack of indium GaN quantum dots nanostructures. The height and diameter of quantum dots has been determined from scanning transmission electron image using the variation of the contrast. And the density of the quantum dots have been measured using atomic force microscopy. Indium side fraction of this sample has been calculated from APT analysis, and the result is presented there. And what we can see that there is variation in composition along in-GaN quantum dot layer. And if we apply threshold on the indium side fraction, we can evidence inhomogeneous distribution that show either a quantum dot or either weighting layer. Now, we have measured the emission wavelengths using cathodoluminescence spectroscopy on a tip-shaped sample, obviously including the structure that has to be analyzed. And we observe two emission range. The lowest one is attributed to gallium nitride buffer, and the highest one is attributed to quantum dot nanostructures. Then, Venn diagram of these structures has been simulated using a NextNano software and using a model structure that takes into account dimension from STM and compositions from atom probe tomography. And from that kind of simulation, we can extract simulated wavelengths, and we can also extract electron and all probability distributions. And what we can observe, what we can extract is the simulated wavelength, which is in a perfect agreement with experimental wavelengths. And the behavior of quantum dots is confirmed by overlap between electron and all distributions. So this means that this methodology that has been developed accurate our simulation model and can give prediction on future growth of devices. So the last example that I will show has been performed on boron investigation in a simple silicon nano devices. And I will show you that it requires both electron tomography and atom probe tomography in order to obtain an almost complete view of the devices. So this is the dedicated devices. It is very simple. This is a silicon gate which has been done by boron implantation and then surrounded by silicon oxide. A tip shape has been then prepared, and STM image confirm the presence of the device within the tip. And the bright and dark contrast have been respectively attributed to silicon and silicon oxide. Then we have performed electron tomography to get access to the morphology of the devices. And after segmentation of volume intensity, we can easily extract silicon oxide contribution from silicon. But obviously, we can't have access to boron information. After electron tomography experiments, atom probe tomography has been performed on the same tip. And this is the result of APT when we are using standard reconstruction algorithm. Even if we are able to detect boron within the device, we can see easily that the devices is distorted from the original ones. So if we want to get accurate and reliable information about dopants, we have to minimize this distortion. So we correct this distortion, at the first order, by using advanced reconstruction algorithms, which are based on correction of the atomic densities. And the best APT parameters have been found by matching electron tomography volume with corrected APT density volume iteratively up to find a convergent solution, as it is shown on the right of the slide. And now we can be more comfortable to extract concentration and dopant profile. So now I would like to speak a little bit about artifacts and limitation of APT. So the main artifacts are a distortion of a reconstruction from the original structure. So this is a reconstruction, this is a standard reconstruction of the previous devices. And this distortion are also present when we are also working on other devices. So I won't go into the details, but you have to know that most APT artifacts originate with a difference in the evaporation fields between different phases. So as an example, if we take these devices, so this is a silicon gate which is surrounded by silicon oxide. Evaporation field of silicon oxide is higher than evaporation field of silicon. So during the evaporation, the ion trajectory of silicon are compressed by silicon oxide. That's why our device is distorted. And this is the same thing for these devices. So we know that these artifacts are present from devices, and we have to be aware of that, and we have to be very careful for extraction of reliable data. Now, if we speak a little bit about limitations, we can say that there are both instrumental inherent limitations and sample-dependent limitations. If we speak about instrumental limitations, obviously APT suppliers are working very hard to minimize these limitations, but we can mention the detection rate, which is not 100%, which is lower. As an example, the APT, which is set up at Civil Grenoble, have a detection rate around 60%. The preparation time could be time consuming. It depends on your sample. It can be between, let's say, 2 hours and 1 day. The analysis volume is quite small when we compare with electron tomography and X-ray tomography. And obviously, it is a destructive technique. Now, considering sample-dependent limitations, we can mention the yield, which is mainly dependent on the electrical conductivity of the sample. We have mentioned previously a distortion. There can be an element overlap, especially when we consider silicon and nitrogen. And also there can be some composition biases. But with a lot of effort on methodology, this limitation on sample dependent, this limitation can be decreased. So to conclude, I would like to remind you that atom probe tomography can be a unique technique that gives a three-dimensional chemical map of spaces with sub-nanometer resolution. Quantitative information can be extracted. And it is very relevant to correlate different microscopy and spectroscopy techniques, especially for 3-nitrile structure or nano structure, to correlate physical, structural, and chemical signature. When we are working on devices, it requires both a 2D or 3D transmission electron microscopy combined with atom probe tomography in order to access both at morphology and chemical composition. And also, this combination allows atom probe artifacts to be minimized. And we have to be aware about artifacts and limitations of these techniques. So I would like to thank all these persons who have contributed to this work. Thank you very much.
Thanks, Adeline. Thanks, Adeline. That was very interesting. I want to remind again, as I said at the beginning, this atom probe microscope is one of the many characterization techniques available through Ascend Plus. So if you are interested on this or in any of the others that you can find in our website, in our online showroom, contact us and we'll try to find out how to, we can show you how to go about it. What I propose now to do is to, if anyone has any questions, could you please turn on your microphone and your camera and you can ask any questions for Adeline. I think we had received one of the registrations, but I think probably you had covered. It was just what were the limitations and challenges. I think you had covered it. Yeah, there's definitely, it's a very, very interesting technique, but obviously you had to keep into mind the limitations that you mentioned there. So obviously you cannot do absolutely everything, but now say you want to add more that on the limitations and on the challenges.
Sorry, Nicolas, I didn't hear what you said.
Oh, sorry. No, when people register for the webinar, we asked them if anyone had any questions. Yeah, so the only one I think you had covered it already was mostly asking about the limitations and the challenges of the APT technique. So I think you had covered it quite well in the second last slide. So thanks. Yeah. Is there any other questions or any comments from the audience? What I would do, so sorry then, I think there's no point in just waiting here doing nothing. If you can think of anything, any other questions, you had my contact details from the registration, so you can think of anything that afterwards, just send me an email and I'll pass them to Adeline and hopefully we'll be able to provide an answer. So if that's it, I think we'll leave it like that. Thanks again, all of you, for attending. I know it's getting into the summer holidays and it's harder for people to have time and to be still at work. So thanks again for your attendees. And I was saying, please, if you are interested on the technique, contact the Ascend Plus access team and we'll see if we can provide you access to it. So thanks again to everybody. Take care. Bye-bye.
Bye-bye.
Yeah, thanks, Adeline.